This video will cover section 10.4, which is mathematical induction. And so we're going to learn how to do some proofs. But before that, we're going to go over the basics, okay? And just like I was showing my students with the Elmo, the camera, that you can prove, you start by, and I was using dominoes. So if you touch one domino, it's going to fall. If you touch two, the second one is going to make the first one fall. If you touch the third one, it will make the second and the first one fall, and so on. So we're going to do something similar here by substituting the numerical values that are given for n. So we're going to start with n equals 1. And so that will be the statement s sub 1. So for that one, we know it's just equal to 1. And now I'm going to use this formula and see if it is true. 1 times 1 plus 1 over 2. And we know that this will be 1 plus 2 divided by 2. And so that is equal to 1. So we say, yes, it is true. Now let's see if the statement is true for s sub 2. So that means that we're going to take the first two numbers. So 1 plus 2, and we all know that is equal to 3. So now let's see if that will be true with the formula. So s, and this will be the subscript 2, s sub 2 is equal to 2 times 2 plus 1 divided by 2. And so this will be 2 times 3 divided by 2, and so that is equal to 3. So we know that the statement is true for s sub 2. This is like what I did with the dominoes, okay? We're going to get to the interesting part in a minute.
Why do you add what?
Oh, well, that was the question. So we are considering the arithmetic sum of all of a set of integers. So that's why I was adding. And other examples, I will be doing different things. For one will be about factoring. Okay. So for this one, we just like look at the problem, how it's written, and then we decide like what type of operation we will do. The next one is going to be a sum of squares. Okay. So yes, that's going to depend on the problem. All right, now for n equals 3, so we're going to prove if s sub 3 works. So we will take 1 plus 2 plus 3, and we know that that is equal to 6. Now let's see if it is true using the formula. So s sub 3 will equal to 3 times 3 plus 1 divided by 2. Do you guys know where I'm getting this? Okay. Does that anyone? If you're not so sure, I'm looking at this formula here. Okay, so let's go back to the example, and this will be 3 times 4 divided by 2. So that will be 3 times 4 is 12 divided by 2, that is equal to 6. So yes, the statement is true. And now finally, let me have you guys prove if it is true for s equals 4. So I'm going to pause the video. Okay, so we proved that for the s sub 4, it is true, and all the students did that in class. So that is true with the formula. So now let's go ahead and see what we're going to do with the mathematical induction, because we cannot be doing that forever, right? For every single number, because that would be impossible. Okay, so several formulas, real math formulas, have been proven using mathematical induction. And so, like I was showing you with the dominoes, we're going to start the principle of mathematical induction. It states that for involving any positive integer n, for any n, if you could prove that s sub 1 is true, and then here, after that, we're going to make an assumption. We're going to assume that s sub k implies the truth. So this is going to be an assumption. And after that, what we're going to do is prove, and this is what I like to call step 3. I know the book just has 2 steps, but I would like to call this step 3, okay? And so that will be to prove that the statement is true for S sub k plus 1. So the one that is right after this one. So if we can do that, then we will have proven that the statement is true for all positive integers n. Okay, and here we just have a picture of what I was talking to you guys. So if you touched, what will this be? 1, 2, 3, 4, 5, 6, 7. The 7th one is going to knock down the 6th, 5th, 4th, 3rd, 2nd, and 1st. And eventually that will all fall down. And if we have time, I'll show you a video. People love to make videos about that. All right, so again, this is a little repetitive, but what we have here is the same steps that I mentioned before. So we show that S sub 1 is true, then we assume that it is true for S sub k, and then we will prove that it is true for S sub k plus 1. This is a topic that on your textbook is not explained very well. So if you look at the sections, they don't really explain. So if you need help and the book is not good enough for you to look at, make sure you ask, you could come ask me or Jonathan or Ms. Salazar or Mr. Estorga, okay, because he also teaches this class at EPCC. So you could ask any of us. Feel free to ask because it's very new to you, so don't be embarrassed, please. Okay, you guys ready? Yeah? All right. So now here, what we're going to do is we're going to start the proof. And so we're going to start with step number 1. Okay, so step number 1, we're going to show that S sub 1 is true. And I know that the instructions here, it just says to write the 3 statements, but we're going to do the whole thing, okay? Let's just get into it. So that was step 1, so let's see. S sub 1, according to this sequence, will just be equal to 1. Now, according to the formula, S sub 1 will be 1 times 1 plus 1 divided by 2. Okay, and so this is equal to 1 times 2 divided by 2, so that is equal to 1. So we are done. So we could say that it is true. Some books sometimes they like to say the statement holds. Okay. All right, so now let's go to step number 2. And remember step number 2, I told you we're just going to make an assumption. So we're going to assume that the statement is true for S sub k. So if the statement is true for S sub k, our assumption, it states the following. S sub k expanded, it will be 1 plus 2 plus 3. And here I'm going to use the dot, 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 just to imply that there are some terms in between. We don't know how many, but there are some. And my last term will be k. K is just a constant, okay? All right, so since we are assuming, we're assuming that if we substitute k into our formula, and just so we're all sure what formula I'm talking about this formula here, okay? So our assumption is going to lead us to the following. k times k plus 1 divided by 2 is true. Okay, so what we're saying here is that these two statements, so let's just do this. Since we're making an assumption, let's list them this way. If s sub k is equal to this, then s sub k will be equal to that. Okay, that's only our assumption. Now, step 3. Remember, the book is only mentioning 2 steps. I like 3. Step 3 is to prove that s sub k plus 1 is true. Okay. So here we're going to rely on the step 2 to prove this, okay? So we have that s sub k plus 1. I'm going to write it in this form. So it will be 1 plus 2 plus 3 plus ... plus k. And what will be the next term? K plus 1. Okay. So then, Delaney, over here. So then, let's see if we could prove the following. S sub k plus 1, according to this formula, it should equal to this. K plus 1, right? Instead of n, we use k plus 1. Now, instead of n plus 1, we're going to use k plus 1, but then another 1, and then divide by 2. Is this understood? Like, this is the formula that we're using that goes like this. N over 2, and then we have, what is it? N plus 1, right? Is that the formula?
Are you talking about the Sn?
Yes.
They're all over 2.
This formula. So what I did here is I substituted for each n, I substituted k plus 1. Okay? So let's go back. That's what I did here. Instead of n, I have k plus 1 because that's what I'm trying to prove. And instead of n plus 1, I have k plus 1 and then plus 1. This is the plus 1 from the formula. All right, so now from there, we're going to simplify it a little bit. And so that is going to look like this, k plus 1. And here we know that if we get rid of parentheses here, we could add 1 plus 1, right? So that will give us k plus 2. Okay, so I want you to make the following notation on your notes. This is what you need to prove. Okay? We have not proven that yet. That's what we have to prove. Okay? And I tell you that because sometimes this type of problems, you don't know if you're done or not. And sometimes you will be done and you will ask yourself, what did I even do? Okay? It happens. So let's see. What we're going to use is the following. The assumption that we made right here. This assumption, we said that the sum from the terms from 1 to k is equal to that. Yeah? Do you guys remember that? Jessica, sit up. Okay, so now, do you see how we're adding this term now? Okay. So what we need to do is somehow make that statement look like this one here that I have circled in red. Okay? Once we have accomplished that, That's when we're done. So let's see. And by the way, this is S sub k plus 1. Okay, so S sub k plus 1 will be equal to k times k plus 1 over 2. And here, the denominator is equal to 1. So if we want to combine the terms, of course, we have to have same denominator. So the denominator will be a 2. So that means that on the numerator, I need to multiply that times 2, correct? Yes? Yeah? Okay. Now from there, I could just write everything under one fraction. And so this will be k times k plus 1 plus 2 times k plus 1. And everything is divided by 2. Now, let's see, what can we do here? Do you guys see a factor in common? K plus 1, right? So we can see it here, k plus 1 and k plus 1. Okay, so what we're going to do is factor that out. And if we do that, if we factor k plus 1 from here, what do we get? K. And if we factor k plus 1 from here, we get a positive 2, right? So that will be my second factor. And so, we are done, okay? And so that is the end of the proof. Okay, so let's trace our steps back. Let's start from the beginning. So step 1, we proved that it was true for S sub 1. We proved that by using the formula. Step 2, we assumed that the statement was true for S sub k, bless you. So that was an assumption. So if it is true in expanded form, it should be true if you use the formula, correct? So then step 3, to prove that S sub k is true, first of all, you need to figure out what are you supposed to prove. Okay, that's the first step. Well, I'm sorry. We could call this like step, 3.1. So yeah, you do that, and then to prove it, you use your assumption. Remember, this was our assumption. We use that here, and then you add the next term, and then you just work the algebra around to get it to look like that. Now, not every formula is the same, okay? So every formula is kind of tricky. And last night, as I was doing my notes, where's my pre-calc book? Oh, here. So the problem that I'm going to do next, just so you know, I'm just being honest, it took me like all this to figure out how to do it because I forgot. Okay? No, the next one. Yes. It's okay. All right. So let's go to the next problem. Before we move on, I know that it's the first one you have seen, but you probably have a lot of questions, but yes. It's mathematical induction. Like you don't use this in geometry, that I know. Maybe you have. Okay, so let's go to the next one. The next problem is the sum of squares. That's the one that I'm showing you all this work. It's not going to take me all this because I already know how to do it. Yeah.
The section is the one that's like, you don't have to take.
Yes.
Oh,
Okay. Okay, let's go. Come on, guys. So step 1, we're going to show that, and you will have a little chance to do a few on your own, okay? First, we're going to show that S sub 1 is true. And this is a formula that you guys in science school, sometimes I've heard questions like that. Like they name the formula, and then they ask you, is that the formula for the sum of all natural numbers or the sum of all squares? Or, you know, so like it's kind of good to know also. There's also one for cubes, so we're going to prove in a minute. And so for that one, it's pretty simple. S sub 1 is just 1 square, right? And we know 1 square is equal to 1. So now to show that it is true with the formula, S sub 1 will equal to 1 times 1 plus 1. I'm using this formula here. I'm just substituting every n with the number 1. Okay. So this turns into 1 times 2. And here we will have 2 times 1 is 2, so 2 plus 1 is 3. And of course we know that 2 times 3 is 6. 6 divided by 6 is 1. So yes, the statement is true. Now let's go to step 2. And so now we're going to assume that S sub k holds. And so for that, let's write it in expanded form. So 1 squared plus 2 squared plus 3 squared. And here we don't know how many terms are in between, but we know the last one is k squared. Now, since we're making an assumption, let's do it this way. So we will say if n sub k is equal to that, then with the formula, the same formula that we have here, will be k times k plus 1 times 2k plus 1 divided by 6. So remember, we're going to go back to that one, and we're going to use that part when we're trying to prove that the statement is true for S sub k plus 1. Okay, so let's go to step number 3. And so now we need to prove that S sub k plus 1 is true. So I'm going to write it first in expanded form. So we know we start with 1 squared plus 2 squared plus 3 squared plus, we don't know how many terms in between, but we know that we had k squared. And my next term will be what?
K plus 1.
Square plus 1?
Squared. So should it be k squared plus 1?
Yes.
Or should it be k plus 1 and then square outside?
The second one plus square.
The second one, okay?
For the top.
So first we add the number and then we square it. That's the same thing that happened here, right? So it will be k plus 1 and then square. So we also got to be careful with those type of things, okay? All right, so now what we need to prove, let's figure that out first. And this is the step that the book doesn't really help you with. But I've done a lot of these things. A lot of my classes in my bachelor's were about doing those proofs like this. Yes?
Why isn't S sub k, why don't we use k squared?
Here?
Yeah.
Oh, so the thing that we're doing is we're just following the formula. So this formula, I cannot tell you who was the mathematician who came up with it, but I imagine it was the result of a lot of trial and error and proofs and things like that. So all we're doing is just following the formula. So the formula doesn't have a square. But of course, it's an interesting question, you know. But what can I tell you? If you think about all those numbers, even though we're squaring them, at the end they're going to end up being integers. So the square doesn't really become part of it. Once we do the one with cubes, that one doesn't have a cube either. Okay? All right. So let's see. What we need to prove is that if we substitute k plus 1 into the formula, and I do need to look at this one because I don't know it. This formula here. So instead of k, for every k that you guys see here, we're going to substitute that with k plus 1. All right? So it will look like this. K plus 1, and then k plus 1 plus another 1. And then we will have 2 parentheses k plus 1 close parentheses, and then another plus 1. Everything divided by 6. Now I'm going to simplify this one a little bit. So it will look like this. K plus 1 times, here we will have 1 plus 1, so that will be K plus 2. And my third factor will be, if we distribute the 2, first it will be 2K. And then 2 times 1 will be plus 2. And then let's not forget we have another plus 1. So the answer that comes from here, it will be 2K plus 3. Do we understand how I got that 3? Okay, so now all of that will be divided by 6. Right, so now let's see how we're going to get to that. And we're going to use our assumption. So the assumption that we had was that K times K plus 1 times 2K plus 1 over 6. We had made the assumption that that was true, right? That to add the terms from 1 square to K square, we just needed to use this formula. Yes? You guys remember that? So now to that one, we're going to add the next term, which is K plus 1 squared. And so that's what we need to prove. So we need to make the statement that we have here look like this one here. So it's almost like proving an identity. Okay? Don't start complaining. You're getting 4 college credits from this class. So yes, you need to work.
I don't understand where it is.
You don't understand what?
Where we're getting this.
Where we're getting this? Like, I don't understand your question.
Like why did you just add plus K plus 4 squared?
Because that will be the term after. So what you do is you take this part. I cannot say half of it. I could say most of it. You take this part that is in green, and that is coming from here. And that one comes from step 2. Here. And remember, this is an assumption, so that's why we're able to use it. Okay? So that same statement that I wrote here in green is the same statement that I have here. No. We need to make the left side look like the right side, like this side. All right? So it's going to take a few algebra steps. Let's get it done. Okay, so we will have K times K plus 1 times 2K plus 1, everything divided by 6. Now, here we have a denominator of 1, so of course, if we want to be able to combine terms, we need that denominator to turn into a 6. And so for that, we will have to multiply the numerator by 6. All right, so now what we're going to do next is we're going to switch the order of some of our terms. So, of course, everything will be divided under 6, okay? So, for this part, I'm going to rearrange the terms so that they look like this. K plus 1 times K, and then 2K plus 1. Yeah? Can I do that? Yes, because multiplication is commutative. So then we do that, and then on this side, I'm going to write it this way. 6 times K plus 1 squared. So the only thing that changed was the rearrangement of the, I guess, the first fraction. All right, so then to continue, let's do something here first. And so those are brackets. Actually, let's just write it. So what I'm going to do now, I don't know if you guys can tell, but both terms, and I call them terms because they're separated by this plus sign, okay? So both terms contain the factor k plus 1. Yes, can we all see that? Yes, they have k plus 1. So my step is going to be to factor k plus 1 out. So k plus 1. And if I factor k plus 1 from here, what would I get? All of this. So k times 2k plus 1. And if I factor k plus 1 from here, what am I going to get? Plus 6 times what? K plus 1, right? Because here we had it squared. Okay. So now what I'm going to do is I'm going to distribute k to the 2k into the 1. And I'm also going to distribute 6 to the k into the 1. So let's do that. Uh-huh.
You didn't factor a k plus 1 from the bracket.
From which bracket?
The reason bracket.
From this one here?
Yeah.
Yes, we did. This is the one that we factor out. That one was only to the first power, so that's why once it came out, like we didn't have to write it in here. But the other one, since it was square, we had to still account for it inside. Okay? All right. So now inside the bracket, we will have k times 2k. That is 2k squared. K times 1 is k. And here we have 6 times k is 6k. And 6 times 1 is 6. Everything is being divided under 6, or by 6. Okay, so now let's go ahead and combine like terms. And so I will have 2k squared plus 7k plus 6. And so what I'm going to do is factor the trinomial square that I have here. And if you guys remember the stuff that we were supposed to prove, I know it's like really far, but the factors were k plus 2 and 2k plus 3. So we could be hopeful, right? And just hope that those are the correct factors. So let's see if they will work. You know, guys, I know that a lot of you ignore when I'm teaching and you don't like to look at the board. And I'm not just talking about one person. I'm talking about several people in this class, and particularly today. And all I can say is you're not going to understand the homework, okay? So, and that, by the way, that's very disrespectful too. So anyways, the factors that we needed were k plus 2 and 2k plus 3. So let's see if they will work. So if I multiply those, what I'm trying to check is if they are in fact the factors for that trinomial. So if I multiply them, it will be k times 2k will be 2k squared. K times 3 will be 3k. 2 times 2k will be 4k. And then 2 times 3 is 6. So 2k squared plus 7k plus 6. So yes, they are the correct factors. So this one here, it is true. So now, yes, we can say that those two statements are true. So therefore, we are done with the proof. So let's go to the next example. Yes?
How would you know where to put the back bracket? And like how to rearrange it?
To be honest, that took me a lot of trial and error. This is what I was talking about. Yeah. That's what I'm saying. It will help out if you guys pay attention to the class. Don't expect me to help you out when you have your take-home exam
if you don't even like to look at the board when I'm teaching. And just so you know, I'm not talking about one person. I'm talking about several. Okay, so next example. Oh, that one we already did it, so you could look at slide number 1 or 2, I don't know. So let's do that one. And so first thing, step number 1, we're going to prove that the statement holds for n equals 1. Or in this case, for a sub 1. So a sub 1 is 2. So what I'm trying to say is that with the previous examples, we started with 1 plus 2 plus 3, or we started with 1 squared plus 2 squared plus 3 squared. But if you guys notice this series, it starts with a 2. Okay? So when we say, instead of saying s sub 1, we're just going to start with, it's still s sub 1, but I want you to think of this. The first term is not a 1, it's a 2. Okay? Is that clear?
Yeah.
Okay. But the n is still 1. Okay? Because we're talking about the first term, so that's a sub 1. Okay. So using this formula here, so s sub k, s sub 1 will be 1 times 1 plus 1 divided, oh, no division. And if you guys notice, if you had to describe that sequence or that series, because we're actually adding them, what would you call it?
All real.
Well, there's something special about those real numbers, right?
Even.
They're all even, right? So all even numbers or all numbers divisible by 2. So let's see if this is true. We will have 1 times 2, and so that is equal to 2. So we know that the statement is true. But you realize that if you had substituted this 1 with a 2 instead, then the statement would have been false. Okay? So you need to be careful with that. And that's why I encourage you that if you're not sure with your homework, send me a message on Edmodo, but tell me the problem number that you're talking about. Okay, so step 2, we're going to assume that the statement is true for s sub k. So in expanded form, it's going to be 2 plus 4 plus 6. And then the last one will be plus 2 times k. What we're assuming is that if we have that, then by using the formula, this formula, it will be k times k plus 1. And this one is a lot easier than the previous example that we did. Okay, so that was step 2. Now let's go to step 3, and that one is we need to make our we need to prove that s sub k, it does not look like a subscript, so s sub k plus 1 is true. So first I'm going to write them in expanded form. So 2 plus 4 plus 6 plus, and then plus 2k plus 2 times k plus 1. You guys see how the 2 is outside parentheses. Okay, so what we're trying to prove, let's see.
Why?
Yeah.
Why?
Oh, what do I need to prove? Okay, so what we need to prove is this. The s sub k plus 1, if you substitute that in this formula, so it will be k plus 1 instead of k plus 1. Then we have another k, so we're going to substitute that k with a k plus 1. And then we still have another plus 1. So this should be k plus 1 times k plus 2. So that is what we need to prove, okay? So now I want you guys to do it. And so what you're going to do is your assumption. That one goes from here to here. And that one, we assume that it was this. And then we're going to add the k plus 1 term. So what I want you guys to do is to make that statement look like this one here. Once you do that, you know you're done with your proof. You could try to factor something, maybe. It's kind of like, yeah, I know, this one was easy. We're going to do something like k plus 1, k plus 1. Okay, so that one is pretty easy, right? You factor out k plus 1 and you get k plus 2. And so that is what we were trying to prove. So we are done. After you're done, you could use this. Or I need to ask. I think it's D. This is in Latin, but I need to ask Mr. O'Keefe what the meaning is. It's something like nothing else follows, nothing else needs to be proven, something like that. Within those lines. All right, so now that one, we already did that one. Let's go to that one. Let me see if there's something different, because that one is similar to the one we just did. Let's try that one. Example 4. So prove that 2 is a factor of any number written in this form. So give me a number for n, Tony.
1,
Give me something bigger.
2,
Give me something bigger.
6.
Okay, 6. So if I make 6, and this is not part of the proof, okay? This is just for you to understand what the statement says. So that means that if you pick any number for n, like Tony chose 6, if you substitute 6 into this statement, it will be 6 squared plus 5 times 6, right? And so that is 36 plus 30, and so that is equal to 66. Can 66 be divided by 2?
Yes.
Yes, right? So you could factor out a 2, and then you will get 33. So what the statement says is that this is true for any n that you choose. It will work. Do you guys think it's true or not?
Yes.
Okay, so let's see. All right, so step 1, and this is going to be a little different than the ones we've been doing, because the ones we were doing were about sums, right? About additions of sequences or series. So step 1, we're going to show that the statement is true for n equals 1. Okay, and so remember, if we substitute n equals 1 into this equation, we will have 1 squared plus 5 times 1. And so that is equal to 1 plus 5, which is equal to 6. So can 6 be divided by 2? Yes, right? 6 is divisible by 2. Therefore, 2 is a factor of 6 and the statement holds for n equals 1. I'm going to post this video on Edmodo, by the way, and the notes. Okay, so now step 2, we're going to use the assumption. So we're going to assume that the statement is true for n equals k.
These are the same steps, like.
Yes, same steps, yes. They look a little different because we're not talking about addition, about adding the sequence. So if we let n equal k, and if we substitute it into the formula, it will be k squared plus 5 times k. Yes? Okay, so now I'm just going to write it this way, k squared plus 5k. So by assumption, we're stating that this thing is divisible by 2. All right? So now that we go to step number 3, we need to prove that the statement holds for n equals k plus 1. Okay, so we're going to do the following. We're going to let n equals k plus 1. And so we're going to substitute it into this formula here. So instead of k, we're going to have k plus 1. All right? So this will be k plus 1 inside parentheses, and then we square it. Then we will have plus 5, and instead of the k, we will have k plus 1. Okay, so now what I need to do is I need to expand it. And so it will be, if I expand this binomial square, it will be k squared plus 2k plus 1. Now if I distribute the 5 here and here, I will get plus 5k plus 5. Now I'm going to combine like terms, and so I will have k squared plus, actually no, I don't want to do that. I just want to rearrange them. So I'm going to write k squared. After that, I want to write this one, 5k. You'll see why in a minute, or you could already imagine why. After that, we're going to have 2k. And after that, what do I have? A 1 and a 5. What is 1 plus 5? 6. Okay, so now, isn't it true that we made an assumption that said that that is divisible by 2?
Yes.
And isn't it true that you could divide 2 by 2? 2k by 2?
Yeah.
Yeah, right? Could you divide 6 by 2? Yes. So then this whole thing is divisible by 2. So if the whole expression can be divided by 2, what we are going to say is that 2 is a factor of k squared plus 5k plus 2k plus 6. Therefore, the statement is true. Okay, and so we'll finish, and we'll finish the video. I'm sorry, this will be the last problem for this class, and then I can do the next one on Thursday, the last one. What I would like for you to do is that if you could please try to do the homework, or at least open it, and if you want to print it and then see like the proofs that you're going to have to do, and you can come ask me, okay, or Jonathan as well. Okay, so go ahead and hurry up because it's 2:24.